the entirety of the process required for the week 3 activity, choosing your statistical test. So I just thought I'll do that quickly. Right, so the first step, of course, would be to load Spss, a new data set. And we can just pretty much copy the data in the forum thread, go to Spss and paste it. Right, so the next step would be to then name our variables. I suppose participant isn't really important, but we'll just add it anyway. Before and after. Alright, so you could do this manually. So just looking at our measures here. So participant would be it's nominal really. It's not really important. We won't really be using it. It's just an identifier. But before and after are both scales, continuous variables, or variables with continuous data. Alright, so that's set up. And then our first step would be to go to Descriptive Statistics and enter our before and after. Choose our options over here. We want kurtosis and skewness, as well as our mean and standard deviation. Don't really need minimum and maximum at the moment. Really just focusing on our kurtosis and skewness. I'll explain why in a bit. Then we'll save. Alright, so that's our output. Before, a mean of 4.25, after 4.5, both at 20 participants. Standard deviation for before is 2.27 and after is 1.96. So looking at our skewness and kurtosis scores, we have before has a skewness value of negative 0.13 and after is negative 0.466, and kurtosis we have negative 7.75 and after less than 0.00. It's unlikely that it's completely zero. It's probably just so far down the decimal points we don't really need to interpret it. So for our purposes, we would just report it as less than 0.0001. Similar to how we report probability values. Alright, so let's get back to this then. So what exactly are skewness and kurtosis? Let's start with kurtosis as an example here. In statistics, kurtosis is a measure of the tailedness of the probability distribution. Right, so the tailedness is pretty much the spread of the line or distribution line. As you can see, the lower levels of kurtosis, the more spread out those tails are. As we go from a platykurtic distribution, which is less than 3, to a mesokurtic distribution, which is a 3 exactly, and the elliptokurtic distribution, as kurtosis increases, the tails become much more narrow within the table, within the distribution. So next we have skewness, and in statistics theory, skewness is a measure of the asymmetry of the probability distribution. So the symmetry of the distribution really refers to how much it represents a normal distribution. And a normal distribution with a mean of 0 and a standard deviation of 1 looks like this. So it's got quite a widely spread tail, and the peak is in the mean. So the highest point in the distribution in this case would be on a mean of 0. So that's a pretty good idea of how a normal distribution would look, a perfectly normal distribution. We don't find them very often, that's why we have a leeway, I suppose. So as you can see, as that the skewness, I suppose, is more positive, the distribution would lean towards the left side. So the highest point is very far along on the left side of the x-axis and far up on the y-axis. So a skewness of 0, that would be more indicative of a normal distribution. You can see the comparison of 0 looks very much like a normal distribution. So as opposed to a non-skew distribution, if it's a negatively skewed distribution, we would see that the highest peak in the data is on the far right side of the x-axis. Right, so I hope that clears up a little bit of the, I suppose, confusion that might have existed with regards to what these two statistical terms mean. And yeah, let's get started on the more thorough analysis. Okay, so the next step in our test of normality would be converting those skewness scores and kurtosis scores into z-skewness and z-kurtosis. So essentially what this z means is that it's converting the values so that they can fit on a normal distribution which has a mean of 0 and a standard deviation of 1. So by converting our raw data values into z-scores, or at least the skewness and kurtosis, we can kind of see where they would fit on a normal distribution. If the fitting is too far to either side, both the positive or negative fitting, either the left side or the right side of the graph, then they would fall outside of what we accept as a normal distribution. And in that case, parametric tests, which are designed on the assumption of a normal distribution, will no longer be applicable, and non-parametric tests, which allow for non-normal distributions to be used, will need to be utilized instead. So essentially, as I posted on the thread, the calculations are as follows. So basically our skewness score divided by our standard error of skew gives us our z-skewness, and the same situation for kurtosis. So if we go back to our output, we can see both our skewness and kurtosis statistics as well as their standard error. So I've just done the calculation quickly here in Excel. So dividing skew by the standard error of the skew would give us a value of a z-skewness value of negative 0.025. And you do the same things for both outcomes that we're looking at, so before and after, for both the skewness and the kurtosis. So these are the final values that you want to be reporting. And if these values exceed 1.96, which within the normal distribution, or the t-distribution, is our approximate value of significance, statistical significance, at the 0.05 level. So if these values fall between plus minus 1.96, we would say that the probability of the distribution being non-normal is greater than 5% or 0.05, and therefore the test itself is not statistically significant, and they fall within our normal parameter values within the normal distribution. Okay, so that's how we calculate that's how we test for normality using this method. And another method, which I suppose is more commonly used, but both of these methods are important, especially when doing your reports, is the KS and SW tests. So we will go to Descriptive Statistics, explore, add our dependents, or add before and after to our dependent list, or worry about factor and label cases. You need to display both the stats and the plots, and for plots we will go to tick the normality plots with tests. Right, so we're looking at here the tests of normality. So the KS test is, or should be interpreted when you have a sample size of 100 or more, and if your sample size is less than 100, focus more on the Shapiro walk, or the SW test. Now, we're going to be looking primarily at the sig outcomes, our significance, our p-values, and if these values are less than 0.05, as it shows on the KS test here, this was 0.03, the hypothesis that these values or this data is normally distributed must be rejected, i.e. the data is not normally distributed. As you can see, we have a sample size of 20 for each of the conditions before and after, so we would focus more on the Shapiro-Wilk test, and sig is much greater than 0.05, and therefore we can assume that this data fits within the boundaries of a normal distribution. Okay, so that's the other way of doing the test of normality, but again, both are important and you need to know how to do both. That's normality done. So just as an example of how you can report these outcomes, I just put this table together. So the descriptive statistics for memory test before and after alcohol consumption. So before we have a mean of 4.25, a standard deviation of 2.27, z-skewness of negative 0.2, z-kurtosis of negative 0.78, a KS test significance, and SW test significance. So this basically tells us what the average score was, the variance within that score, and whether the data was normally distributed. And we get the same values for the after as well. So essentially this, out of all that you've done, this is what you need to report. Unless of course you're required to show your SPSS output. So yeah, I hope that video helps clear things up a bit. And good luck for your ethics proposals.